Uh, 21, this is on page 3. I just want to point out, okay, so if we see a radical above and one that's not below, or vice versa, there's a radical above and none below, and but after you clean everything up, your degrees are the same, you know there's going to be split asymptotes on both sides. And I think when I was walking around, it looks like you guys were getting it, after you find the ratio, you're going to also create the opposite sign of the same ratio. There's going to be split asymptotes. I just want to point out a minor thing here that your limit is 4/5 and -4/5, but if it's asking for horizontal asymptotes, these are asking for lines. So then we want to make sure we indicate as y equals 4/5 and y equals -4/5. Okay, so limit is just the value, but then asymptotes is a linear equation. So make sure you name it or call it as y equals. 22. Anybody have any trouble with these problems? All right. So, you'll see something like this on the test, and this is where I feel, students have a little bit more trouble. And I think that's just because, students either want to plug in a decimal or they want to plug in 100. And as long as we don't do that, I think we should be able to get through these processes pretty well. One thing to highlight is if we're asking for a limit approaching a number, order pair is never going to tell us anything, right? If it's asking for a limit, we got to look at connected parts of graphs. So you may be tempted for limit as x approaches 2 to just, oh, that's 2 is 12. I want to go to 12 here, but these are just order pairs. We have to look at the approach from both sides. So yeah, if you feel good about this problem 22 and you get your steps, I think this is the hardest part of the test here, just being able to recognize, how to pull information from the piecewise function, and that order pair is never going to play a role in finding your limits. And then if it's approaching a real number, you're always going to do direct substitution first. And if you see infinity, negative infinity, you're always comparing degrees first. Okay. I also want to talk about the graph for a moment here. This is page 23. Sorry, not page, number 23 here. Anytime we're approaching positive or negative infinity, we're asking for the behavior as we exit the graph. So if we're approaching negative infinity and if equal to 8, we know that however way we want to, the graph is going to end up flattening out as it exits from our view. And here, limit as x approaches positive infinity is negative infinity. That means as we move to the right, our graph is headed down towards negative infinity. There is room for interpretation. So for f, limit doesn't exist. You can do one of 3 things. If a limit doesn't exist, you can make it a jump discontinuity, where you force the graph to jump from one branch to the next. You could also make the graph a vertical asymptote. You could also make the graph an endpoint, stop there, and then maybe pick up at a later point. So if the limit doesn't exist, you can do a number of things and still earn full credit. Okay, so it's a very general statement. What you don't want to do is you don't want to do this. You don't want to make the graph look like this. Okay, so if you make the graph look like that, then you're making the limit exist. Okay, so if you just put a hole there, that's not going to be one that fulfills that condition. Any questions about grading the graph? Another thing to watch out for is if your limit exists, like negative 6,4 here, we don't want to do this. Make sure you don't put arrows like this. If you do that, this looks innocent enough, but if you do an arrow in the middle of the graph, I'm going to follow that arrow.
Good morning, Eagles. Could any student that received a map testing task please report to the media center or the cafeteria now? Thank you.
And if you put an arrow in the middle of the graph, I'm going to follow it, and then usually that is going to cause issues, and it's going to end up failing the vertical line test. So you never want to put arrows on both sides. If you're not sure where the graph's going to go, just extend it slightly, and then you can come back to it if you need to. But at least we don't want to ever do that. Right? The only time you should have arrows is if you're approaching an asymptote or you are clearly exiting the graph from view. I think those are the only safe places to put arrows. Otherwise, you're going to run the risk of making it where your graph is going to fail that function restriction. Okay, for 24, says find value of k for which the following piecewise function is continuous. So a problem like 24, you're forcing continuity. You want continuity to occur. And the idea is that you're going to use continuity condition to give you that framework to help you solve for k. So if you just step through continuity condition, eventually you're going to be able to solve for k. So for instance here, if I want to go through continuity conditions, I know that the x value in question is -2. So if I do f of -2, that goes into the first piecewise, and I get 2 times -2 plus k, -4 plus k. That's unresolved, but we keep going. Second condition, does the limit exist? We have two different functions split on either side of -2. So I do have to rely on one side of limit. I have to do a limit as x approaches 2 from the left for 2x plus k, 2 from the right for kx minus 3. I plug both in, and if I want this second condition to pass, I have to get them to equal to each other. So if I set them equal to each other, I can solve for k. Once I solve for k, then I found my answer. So you're just using continuity condition to help you eventually solve for your missing constant. So sometimes continuity conditions are used to show if a function is continuous or not. Other times you're using continuity conditions as a framework to help you solve for a missing value to allow for continuity. Okay, there's question about 25. So let me work through that one. Page 4. Verify intermediate value theorem applies to the function x squared plus x all over x minus 1 on 3/2 to 4 for f of c equals 6, and then find the c value. So IVT is asking, can we guarantee this y value of 6 somewhere along this interval? And we want to go through our conditions. So the first condition is our function continuous on our closed interval? The only continuity issue we're going to have is going to be from the denominator. Okay, so there's a continuity issue. What's going on? What's the issue here? Vertical asymptote at x equals 1. If there's a vertical asymptote, does that mean that IVT is going to immediately break down? No. It's a potential red flag, but this is only going to impact us if this is interfering with our interval. If this asymptote is somewhere in between the interval, then that's an issue. Then IVT breaks down, and then we can say that IVT doesn't apply because it doesn't pass the first condition. But if the only break in the graph, the only issue is clearly outside the interval, because 1 is not between 2.5 and 4, we're safe. Okay? So as soon as you see that there's no issue, you don't have to explain, how you know that. You can just do a visual check there, but you do need to indicate, if you want to continue with the theorem, that you have to state that your function is continuous on this interval that we're working on. All right, so it passes the first condition. And then the second condition is, are my endpoints going to sit clearly above and below that y value of 6? So I have to plug 5.2 in for x, and I have to test those points. So I need to find f of 2.5, which is 2.5 squared plus 2.5 all over 2.5 minus 1. Now, I know this is a little bit messy here. On the test, if I give a problem like this, I'll make it where it'll be easier for you to numerically figure out, because you won't have a calculator. So I'll give you ones that'll be easier, to resolve. But this ends up giving us around like 5.8, and 5.8 is under 6. So that's a start. What do we want then from f of 4? What do we need from f of 4? Above 6, right? If I'm going to guarantee a y value of 6, I have such a limited view of the problem, we need the endpoints to be above and below our target. If I start at 5.8, I need to end up above 6. If I start at 8.6, I need to end up below 6. So f of 4 would be 4 squared plus 4 all over 4 minus 1. This is 20 over 3, which is around 6.7. So we're safe, right? We're starting at 5.8, no breaks in the graph, and we end up at 6.7. So 6 is clearly between 5.8 and 6.7. Just make sure that you're comparing apples to apples, right? We don't want to say, oh, 6 is not between 2.5 and 4, and therefore this breaks down. You're not comparing the same values here. This is the y value, and these are x values. So make sure that we're always comparing y values with y values when you're doing IVT. So we can say by IVT, since f of 5 halves, which is 35 over 6, is less than 6, which is less than the other endpoint, 6.7, which is coming from f of 4. And then this is a statement that shows the relationship that the intermediate value is clearly between the two endpoints y values, and that the endpoints y values are coming from these endpoints. Therefore, we can guarantee f of c equals 6 on the interval from 5 halves to 4. So that's the first part. The second part is, well, we know that there is that y value of 6 somewhere on the graph, and now we just have to go and look for it. And to look for it, we just have to basically set that y value equal to in for y and just solve for x. So I'm just looking for order pairs here. I know what the y value is. I'm looking for the x. So I'm just setting the function equal to 6. X squared plus x all over x minus 1 is equal to 6. Algebraically, I'm just cross multiplying, bring everything over to one side. I'm factoring, I'm solving, and my c value has to live between 2.5 and 4. So 3 and 2 are my candidates, but not both of them fall inside the interval. Only 3 falls between 2.5 and 4. So I'm only going to keep x value, or c value is basically the x value solution of our problem. So IVT is not hard, but it is a little messy in the way that we write our justification. And don't forget to write your continuity statement. Okay, so I see a lot of students on the test, they do everything right, and they just didn't write that continuity statement, and they end up losing a point. So, but this is a good framework for later on. We're going to do future theorems that kind of follows this pattern, where it's check for continuity. And then when you find your solution, you need your c value to live between your endpoints. So, we're establishing these similarities for future theorems. Okay, any questions? Page 1 through 4. So again, this is what your test will look like, page 1 through 4. And if you feel pretty good about it, it should, I mean, obviously, we still have a lot of days to, few more days to review. But if you feel good right now about page 1 through 4, that should give you some confidence that you're about ready to take the test. But obviously, we want to spend some more time just to kind of fine tune and make sure we know everything. But okay. No other questions? Our homework is pages 7 through 11. So going to have us go ahead and start on page 7. The keys are attached, but I'm going to kind of pace us through this time that we have. So I'm going to have you guys start on page 7. You guys can, work together, or you guys can have conversations and work together. But, after like 5 minutes, I'll put the answers up and I'll go through any questions you have, and then you guys will continue working. Okay. All right, go ahead and start. Yeah, but I should have keys attached for everything in your packet. And I'll walk around to see if you have any questions. Any questions with number 1, A through G? Let me just review. This is on the back of your test review packet. Just to remind us continuity conditions. First is the point defined. Second, does limit exists? Sometimes if the piecewise function has less than greater than, you may have to go kind of explore a little further and rely on one side limit before it can confirm whether that limit exists. And if all 3 conditions pass, obviously function has continuity at that point. If the second condition fails, we stop and we say this is a non-removable discontinuity at x equals c. The limit doesn't exist. So either the graph is disconnected or there's a vertical asymptote. We only go to the third condition if the second condition passes. If it passes the second condition but fails the third condition, we consider that a removable discontinuity. That means there's a hole there at that point. Now, if you're deciding between these types of discontinuity, we have to make sure we get past the first condition. So it doesn't matter if we fail or pass the first condition, we always go to the second one. Okay? Obviously, if the first one fails, you already know that the function is not continuous, but you still don't know what type of discontinuity. So we still have to go to the second condition. Regardless of the fact that even though we may already know the function is not continuous, the only way to confirm what type of discontinuity it is, we got to at least reach the second condition. Okay, so for number 2, we have a greater than less than. So we know that we have 2 different branches graph on either side of 4. So if we go through our continuity conditions, first condition, does the point exist? Second condition, we do need to rely on one side of limits because we have 2 different connected parts of graph on either side of 4. And we evaluate the limit as x approaches 4 from the left and from the right. See if they are in agreement. They're not in agreement. The one side of limits are not in agreement, therefore the full limit doesn't exist. And if the second condition fails, we consider that a non-removable discontinuity. Number 3, it's also a piecewise function, but notice this is a doesn't equal to versus equal to. And this is different than less than greater than. Less than greater than, you have 2 separate branches of graph. Doesn't equal to means you have a point in the graph. So if you see a problem like this, there's no need for one side of limit because on both sides of -1, it's the same graph. Less than -1 is the first one. Greater than -1 is also the first one. And that's just a singular point. So the point exists. Second condition, does limit exist? There's no need to do one side limit. Just find the limit of the connected parts of graph. As x approaches -1, do direct substitution, you're going to get 0 over 0. You can go through factoring, reevaluate, and get -2. The limit exists, we keep going. The third condition breaks down. Remember, I think some students, they get to the third condition and they feel, wait, what do I need to do with the third condition? You're not creating any new data. You're just going back and comparing between the first 2. But also I'm looking for you to write it in a specific notation. I don't want to just see 3 doesn't equal to -2. I know what you mean by that, but this is a more a better way of representing that third condition. Say f of -1 doesn't equal to the limit as x approaching -1 of f of x. And again, if you want to write a limit statement, make sure that you don't just write it like this. This is the incomplete. You gotta have something here. So. Well, I'll point out, a lot of students leave this notation out because we don't say it this way, but we always have to indicate what function you're referring to if you're evaluating a limit.
It's reading.
Yeah.
Since the default is named geodex for your.
Oh, sorry, yeah, you're right. This should be geodex.
Okay.
Yeah. Okay, page 9. If we're approaching negative infinity, we want to choose the appropriate piecewise function is the x plus 5. What do we do if we're approaching infinity? We always do what? Compare degrees. You don't see anything in the denominator, but we can always force a what below? 1. And so here you can tell, okay, obviously my degree is higher in the numerator. And so it's either plus or minus infinity. I can plug in a -100, and -100 will show me it's a negative value. So therefore, negative. Again, part D, students get thrown off with part D because they say, oh, great, approaching 2, that's going to be 11. But this is an island here. This is not a connected parser graph. We have to look at where the graph is approaching on either side of 2. And from either side of 2, one's headed towards 7, the other's headed towards 3. This is obviously, the arrows are not pointing towards the same y value, and therefore that's why the free limit doesn't exist. Again, approaching 5, the order pair is sitting up here at y value of 20, but both sides of 5, the graph is approaching the same y value 9. So the one-sided limit is kind of like the arrow version of the graph that we've been doing on the first day. Approaching infinity, again, we want to compare degrees. There is no denominator, but I can force a 1 below. The numerator still has a higher degree. I'm approaching infinity, so I'll test 100. I get a positive over a positive, so therefore positive. For 2 and 3, you're stepping through continuity conditions. Again, when you're writing your limit notation, make sure you indicate what function you're referring to. A lot of students want to leave these out. Part B, you're also using continuity condition, but you're using it as an equation solving tool to eventually solve for K. So for number 3, it's just a framework to help you set up so that you can eventually solve for K. All right, let's practice sketching a graph. Page 11. I like to start with order pairs. Those are the easiest ones to get going. If your limit as we approach negative and positive infinity equals a number, that means these are horizontal asymptotes. So you know that this is a guide to show you how your arrow is exiting as we follow left and to the right. So I like to, if I know there's a horizontal asymptote, I just like to just put a dotted line and don't have to worry about stretching it all the way across. There's going to be different asymptotes on both sides. So I have one indicating how my graph is going to look on the left. And then on the right, I know my graph is going to eventually end up heading out, getting closer to that dotted line. I see some students, they want to do a dotted line all the way across, but these are just asymptotes for these individual end behaviors. So you don't have to do dotted line all the way across. It doesn't apply to the other side for these piecewise functions. And if the limit ever exists, I like to always just start off with a hole at that point. And then that just feels like the safer route to go. And then you can fill it in if you need to later on. Make sure that no parts of your graph is failing the vertical line test. I do want to point out again with vertical asymptotes, careful how you draw your arrows. So I do want to point out, this is what I see some students do. Around an asymptote, say this one here, right, approaching 4. Make sure that your arrows are gravitating towards the dotted line. Okay, I see some students do this. They have the asymptote here, and they end up drawing it like this. This is not approaching negative infinity. Okay, make sure your arrows are headed towards and not away from each other. This is not representative of that behavior. If a limit doesn't exist, you can make it an endpoint. You can make it jump this continuity and make it a vertical asymptote. So we have a couple of options available if the limit doesn't exist. Okay, just a few more minutes. On page 19, I have your test topics. So, we still have 2 more days. I mean, tomorrow we do need to start unit 2, but we can I can come up with some more problems second half of class tomorrow just to have us more practice with more of these topics. Help sessions. So I'll have a help session tomorrow morning, 7:30 to 8:15. And then Thursday, abbreviated one, 7:15 to 7:40. We can go over some additional problems in this packet that we may not get to, as well as page 31 to 35 from your test, from your unit 1 limits. There's just additional problems that I didn't assign for homework, but we can go over in help sessions if you would like. I'll also send out a Teams link tomorrow morning, if you want to join online. I can answer questions virtually as well. Okay, your homework is to finish up to page 11. 7 through 11 is your homework.
I did one.
Okay, appreciate it.
That's the old ones.
I'll mark it down. Thank you.
She's like,
You're like Oh, yeah. Yeah. They have a crazy thing. I'm down. You're saying, I might go. Yeah. That's late. They go late. The lunch on the other.
Sorry, she's.